we now? This is why we do training, isn't it, and dry runs, so everything goes well on the day. So yes, hello. I am the current president of the ICT. I took up this role just at our last convention and AGM at the end of May. I'll have this role for 2 years, and I'll be succeeded by the current vice president, Veronica Elmarkova from Wholesome. So great welcome to you all today, and congratulations on our CyPro committee for putting on this excellent webinar and our two great speakers. So I will let Anita introduce those in due course, but just to give you some background about our mission as the ICT, if you're not already aware of what it is that we do. But essentially what we're trying to do is improve the role of concrete technologists and the standing of concrete technologists worldwide. And I think this is increasingly important as we look towards newer low carbon concrete technologies and changes within concrete technology. So I think we as concrete technologists have a vital role to change an industry going forward, and the ICT is here to support the evolution of your careers and your knowledge and the stages that you go forward through. And the point about worldwide is very important to us as a global organization. You can see in the red where our memberships are. If we're missing any red, do please let us know, and we encourage any of you who are not currently members to do get involved and join us as we go forward on this big mission. We do have our 4 stages of entry for the ICT. You have a stage 1 general practice, all the way up to stage 4, the advanced concrete technology diploma. And this is the MICT, and very big news for us is that this has now moved to Heriot-Watt University and is taking enrollments in September this year and again in January 2026. So if you're interested, please take the time to look this up and get involved with the ICT at different levels. With that, I'll hand over to Anita and let you introduce the speakers and the event. Thank you.
Hi, thanks, John. Good afternoon, everyone. I am Anita Mary Joseph, the outgoing secretary of Institute of Concrete Technology Student and Young Professional Network. I'll introduce CyPro to you, Student and Young Professional Network. So the aim of CyPro is to attract young talents to the concrete industry, give them peer support, CPD opportunities, and help them to find and grow within the wider concrete industry. So it shows how to join CyPro and why you should join us. If you're a student, you'll get free membership. In a way, you can learn from experts in the field, build networks and connections both nationally and internationally through various in-person events that we organize. You'll also get CPD opportunities through workshops and webinars like this one we are organizing now. How to join? You can go to the ICT website, select Young Connect. There are 2 applications forms. One is for students. If you're a student, you can fill out the student application form, or the normal one if you are a young professional. If you want to contact, get in touch with us. We are present in various social media platforms. We are in LinkedIn, Instagram, and YouTube. So let's move to our first presentation. I'll introduce our first speaker. So our first speaker is Dr. Harshita Garg, who's a technical manager at Brett Concrete. She's also an architect and did her PhD at University of Leeds. She's also the chair of CyPro. Today, Harshita is going to present to us on AI-based approach for predicting the performance of Abercorn Bridge. I want to introduce to you also the book written by her. She's an author of a children's book on concrete, Joy and Love's Big Concrete Adventure, which is available in Amazon right now.
Good afternoon, everybody. Can you all see my screen?
Yes.
Thank you, Anita, for the introduction. My name is Dr. Harshita Garg. I'm technical manager at Brett Concrete, also the chair of ICT CyPro, as Anita has mentioned. Today, I will be presenting a part of my PhD work, which is automated artificial intelligence-based approach for predicting the in-service performance of Abercorn Bridge. It was under the supervision of Dr. Srijit from Queen's University Belfast, Professor Vasilis and Professor Anthony Korn from Leeds University, and Professor Mohammad Bashir from Heriot-Watt University. Let me begin by saying that if you can predict it, you can prevent it. And that's the rationale behind structural health monitoring. So what is actually structural health monitoring? So it's an innovative technology that automatically sense, provide, and evaluate timely information on physical and chemical changes in materials that could allow early detection of deterioration, such as chloride-induced corrosion. So basically, we have sensors such as electrical resistance sensors, temperature sensors, relative humidity sensors that are embedded in the concrete or concrete structures. The data from these sensors goes to the data acquisition system, which store the data remotely on the remote desktops. And the data can be then pre-processed and cleaned for analysis. And the data analysis could provide us timely information about the faults in the structures, and which can help for decision making and planning and maintenance strategies. Therefore, it leads to real-time maintenance, increased serviceability, and improved safety of the structure and the environment. While global SHM has been in use and people know about its benefits and its potential applications, the local structure health monitoring for durability is still not the predominant practice in the maintenance management of the structures. But why? What are the factors which lead to companies and stakeholders to not adopt SHM? So there are three primary factors, first of which is stakeholders. So not all stakeholders have the knowledge about structure health monitoring and what are the benefits associated with it, and therefore they are reluctant to any changes. Secondly, even if they know about SHM and they implement those sensors in the structure, these sensors generate huge amount of data, which is difficult to analyze and maintain, and therefore they cannot get useful information from this collected data set. And finally, the cost of these sensors, which increase the overall budget of the project. So these three are the factors which does not allow stakeholders to use sensors. In this presentation, I'm focusing one of the topics here, which is complex data processing, which indirectly serves the other two as well. So sensor data dilemma. So the current practice of collecting massive uncertain sensor data has some issues. Here you can see that this is the original data that we get from the sensors. And you can see here that there is some missing information. There is huge cyclic pattern uncertainty in the data. So this leads to, which is difficult now to process it. It is also not easy to identify what actually is the defects from these noise. And finally, if you find wrong information from the data set, that could lead to wrong judgment and therefore some untimely maintenance and repairs that could eventually increase the cost of maintenance and does not solve the purpose of using the sensors. So therefore, this needs some solutions. So the three potential solutions that were identified were: first, to develop the AI-based SHM methodology that could resolve any issues related to data processing. Second, to conduct whole life cost analysis of the concrete bridges with various SHM systems for durability over a specific period and therefore eliminate any cost related issues. The two of these can then assist decision makers in making any decisions about repairs and maintenance, and therefore eliminate any barriers preventing the widespread adoption of SHM. So in this presentation, I will only be discussing about one of the solution, that is AI-based SHM methodology that I developed. So the aim of the research was to develop an automated AI-based SHM methodology for analyzing and interpreting the SHM data from a bridge in Northern Ireland, that is Abercorn Bridge, for predicting its in-service performance, and therefore to demonstrate the reliability of such a system that could contribute to the sustainability of concrete structures. So Abercorn Bridge was built in 1932 in Northern Ireland. It's a four-span steel and reinforced concrete combination bridge. So overall, this bridge was in good condition, but over time, it started to show the signs of some localized deterioration, such as cracking and spalling of concrete, which exposed the reinforcing steel. There was also evidence of water damage and staining from all the exposed areas, which led to the compromising of the strength of the bridge. So therefore, the bridge was repaired and the major patches were filled with low shrinkage concrete repair mortar. Along with that, on the bridge deck, it was sealed with the waterproofing layer, while the soffit area and the sides of the parapet beams were applied with breathable protective polymer-based coating so that it allows the moisture to evaporate. In addition to that, during the repairs, 3 commercially available sensors called septopods, as seen here, were installed. So the aim behind installing these sensors was to check the effectiveness of water vapor transmissible membrane on the soffit and the waterproofing layer on the deck surface. Also to see the rate of chloride ingress in the concrete. So what is actually the septopod? So septopod is a combination of 3 types of sensors, that is corrosion sensors, resistance sensors, which are electrodes, and temperature sensors, which are called thermistors. And the set of these 3 sensors are called septopod. These sensors were located at 3 different depths at 3 different locations in the concrete. So these are the 3 septopods here you can see here. The first one was placed at 20 mil from the deck surface near the expansion joint, and it is adjacent to the old concrete. The second one was placed near the deck surface from 20 mil from the deck surface, but away from the expansion joint. The third one was placed at 20 mil from the soffit area. So the orientation of these 3 sensors were first 2 could be seen 20 mil from the deck surface, and the third one is 108 mil from the deck surface. So each septopod has 6 electrodes at 6 set of 6 electrodes at 6 different locations and 3 temperature sensors. So these first 2 were oriented to capture changes in resistance and temperature near the deck surface and the soffit of the bridge, while the third septopod was specifically placed near the soffit to check if the moisture was properly evaporating from this area. Now, the sensors were capturing the data for over 4 years. So we were collecting data every 2 hours for the first 20 months. The remaining 40 months, the data was collected twice a day, that is at 12 a.m. and 12 p.m. Every day the data was being collected for the remaining 40 months. So this is the original data that we got. This is the raw typical data of electrical resistance that we got. And here you can see that there is missing data, the single lines. Here the data is going up and down. There's uncertainty in the data. There's cyclic patterns. So, and the data in itself is huge, and it is difficult to manually analyze it, and it is also time consuming. Therefore, all this led to the use of some algorithms which could help us in processing it easily and efficiently. So For this, to analyze this data, an automated clustering-based linear regression was used. So it is an amalgamation of two algorithms. So this methodology combines two type of algorithms. One is unsupervised learning called clustering, and second is the regression called segmented regression. So this methodology is a 7-step process. So first step is to collect all the sensor data from resistance, temperature, ambient conditions. Second is to clean the data, pre-process it, reduce noise from the data, identify the missing information. So basically identify all the trends, general trends in the data. Then third is to quantitatively analyze the data using these two algorithms called k-means clustering and segmented regression. The results from these two algorithms could be used to calculate diffusion coefficient that is enough to assess the performance of concrete and structures. It can also be used now in any service life model like Duracrete or Life 365 or Klingkong to predict the remaining service life of the concrete. So all these steps I will now discuss it on the sensors data that we have got from the Abercorn bridge sensor data. So the next step was to pre-process the data, and here as we can see that there was huge cyclic variations in 4 years of data. So this is mostly because resistance measurements are directly affected by environmental conditions. And here if you see that with the increase in temperature, there's a sudden drop in the resistance. So due to which an Arrhenius relationship was used, which reduces the influence of temperature on electrical resistance and therefore standardize it to 25 degrees Celsius temperature. Now the huge variations that we saw in the previous slide, they are now reduced. And here it can be seen in the Septopod 3. Those huge variations are now showing that the resistance is overall increasing rather than such varied sensor data. So in this, we can see even though the resistance data is increasing, there is some variation. So resistance data was increasing, and then suddenly there was a drop in the resistance. So this drop was identified from the sensor data, and then on visual inspection, it was identified that there was leakage in the structure in the newly repaired concrete near the expansion joint. So this repair was done soon after identification, and after that, we can see the resistance started to increase again. Even though there is some missing information, we can see that resistance was overall increasing. And then there was the sudden increase in resistance, which is still unknown for the reasons, but there were two major reasons identified. First, during this time, there was a change in the frequency of data collection. So the data was collected every 2 hours, and then we changed it to collecting twice a day. So that messed up with the system, making some, giving us some inappropriate results. Also, the local areas nearby in the bridge were heated up to get rid of some excess moisture. So that could also have led to increase the resistance, but the actual reason was unknown. But overall, the resistance was increasing. The resistance was higher near the soffit, again due to the presence of water vapor evaporating, a breathable coating, and it was lower near the deck surface. So this is all the information that we can get from pre-processing the data, which is a qualitative kind of information. Similar data we got from Septopod 1 and Septopod 2. So, but in order to get further information about the performance of concrete and remaining service life, we need to quantitatively analyze this data, for which now we need 4 different parameters. First is initial rate of increase in resistance, then value of steady state resistance, time taken to reach the steady state resistance value, and finally the value of diffusion coefficient. All these 4 parameters can help to assess the performance of repaired concrete, for which the algorithms, AI-based algorithms were used, called automated clustering-based piecewise linear regression. So I'm going to discuss this algorithm on one of the data sets that we got from the sensors. So because we have seen that resistance data was overall increasing, so I have taken the continuous data set after 650 days after 2 disparities we found, because this was the continuous data for the next remaining 2 years. So this is the data at 70 mil from the soffit area. So here we have variable as standardized resistance. Now, if you see here, if you look at the data set here, it looks like the data is divided into around 5 clusters or 4 breakpoints. So it can be seen here. It is divided into 5 clusters or 4 breakpoints. But how do we know that at what location these clusters are, or how many of these clusters are optimal? In order to find that, we've got k-means clustering algorithm, which has first method called elbow curve method that identifies optimal number of clusters. So basically the algorithm runs for different values of k from 1 to 10, and based on within cluster sum of squares, it identifies the value of ks clusters. Where there is an elbow formed as seen here, it shows that this is the optimal number of cluster called, so there are 3 clusters. Now to cross validate it, we use second method of clustering called silhouette analysis. So this method identifies how similar a data point is within the cluster compared with other clusters, and how well each data point fits into the assigned cluster. So based on this, the highest every silhouette coefficient is considered as the number of clusters required. Keep that in mind. It's not the correct number of clusters. It is the only optimal number of clusters, not the exact number of clusters that could be identified. So now the next step is to run the algorithm with the clustering and piecewise linear regression. So it identifies 3 different clusters at 3 locations based on, so it divides the data into those clusters such that it is based on a change in the slope and change in the underlying trend of the data. And here we can see that it provided me 3 clusters, but this doesn't seem to look that they are correct by looking at the data. So there is a need to put a statistical method to and adjust some criteria that if it passes those 5 criteria or 4 criteria, then the algorithm, the results of the clusters are okay. So the 4 criteria that were set were: if the R squared value is greater than 0 for all the segments. Second, P value is less than 0.05, that is, time has significant impact on the resistance. Third is the absolute square error, mean squared error and absolute error, and the values are closer to 0, signifying that the higher accuracy for segments identified. Then last criteria is these 2 values, MSE and MAE, have no significant difference. So as we can see here from the 3 segments, we have all the 4 criteria, and R squared value is 0 while the P value is greater than 0.05. So because 2 of the 4 criteria were not met, that means the clustering is not appropriate. So algorithm reinitializes until all the 4 criteria are met. So once all the 4 criteria are met, it converges the clusters and provides us the correct location of the clusters and the number of clusters. So here we can see That algorithm was run until all the criteria were met, and 5 clusters can be obtained here. Now, the last two segments, the segmentation, the intersection point of the last two segments is considered as the time taken to reach the steady state condition of the resistance and steady state resistance condition, steady state resistance value, which are two of the parameters to assess the performance. The third is to understand the slope or the change in resistance, which can be taken from the equations for each segment identified. So we have got 3 of the 4 parameters. Now, this algorithm also reinitializes to cross-validate with the increased number of clusters. So instead of 5, it goes up to 6 and cross-validates and check if all the criteria are again meeting or not. In this case, as we can see that it doesn't meet any criteria for 6 clusters. That means the optimal number of clusters were 5. So the values obtained, so that algorithm initializes for all septopods at different locations at different depths. And the results of steady state resistance, time taken to stabilize resistance, and change in resistance were considered. Now, to calculate the fourth parameter, that is chloride diffusivity, there is an established relationship called Ernest-Einstein relationship. dE by d naught is equal to rho by rho bulk. So now we have, to identify dE, we have d naught as diffusion coefficient of chloride in pure water. It's a second, we need resistivity of pore fluid, which can be taken from NIST model using the mixed composition and proportion values. Rho bulk is the steady state resistance value that we have got from the analysis, from the algorithm. So that value is for all the sensors at different locations were put here. And here we can see the results of diffusion coefficient at 3 locations and steady state resistance at 3 locations. So overall, we can see that resistance is increasing with time, signifying that repaired concrete is naturally drying out and there are continued changes in the microstructure of the concrete. Secondly, we can see that resistance is lower near septopod 1 and 2. It is lower near the expansion joint more because the surface layer near the deck has waterproofing layer. Resistance is higher near the soffit, again because of the breathable coating on the soffit, which is releasing more moisture. Also, but overall, repaired concrete can be seen performing well. If you look at the diffusion coefficient values, it is higher near the expansion joint, indicating that contamination in the bridge may arrive from the deck surface. But overall, it was performing well. So now these diffusion coefficient values were taken average for each septopod. And here we can see the 3 values. On comparing these 3 values with 5 category framework for assessing the long-term performance of concrete structures, we can see that it lies in the second one, which is good quality concrete providing good resistance to chloride ion ingress. So this is a further qualitative information that we have got from the analysis. Now, these values can be used in any service life model for service life prediction. Here I have used this in Duracrete modeling to predict the time taken to initiate corrosion. Now, chloride concentration at 45 mil depth for bridge deck surface and soffit can be seen here at 3 different points. 0.4, 0.2, it's the minimum chloride content, 0.4 average chloride content, and 0.6 as the highest chloride content it can reach to. Considering a 0.4 chloride content to reach at that point, it would take around 22 to 27 years for septopod 1 and 2 near the deck surface, and around 53 years near the soffit area. Now, if we consider the 10% as an acceptance criteria for probability of corrosion years initiation, we can see that it can take around 16 to 18 years for chloride initiation near the deck surface, and around 36.5 years near the soffit area. So the expected service life of this concrete so the concrete was designed for 25 years to reduce the refurbishment cost. Now, the remaining service life that we predicted matched closely with the design service life provided by the engineers, knowing that the bridge has already been in use for over 4.5 years. So the remaining service life was predicted quite closely, which shows a high degree of accuracy and reliability of the model compared to human predictions. It also identified that the repaired concrete near the deck would experience chloride ingress sooner than the bridge soffit due to additional salt spray on the deck surface. And finally, the chlorides may start to enter near the expansion joint near the deck surface first. So all these informations are quite useful to inform maintenance engineers when to focus on maintenance and repairs of the bridge. So finally, conclusions. There are challenges that we understood from the sensor data, that it was difficult to handle and manage, and there was uncertainty in the dealing with these large amount of data sets. So that's why we have established this algorithm, and we see the benefit of resorting to an automated approach for dealing with these SHM data from structures. Now, this approach is an alternate to us doing non-destructive and destructive tests by removing concrete from the structures and carrying out those tests in labs and on site for determining the diffusion coefficient values. Further, we also understood that in the initial years, we saw that there was leakage in the concrete, which was a new concrete, and that was detected at the very early stage uh, due to the help of sensors and data analysis. Unless if we would have not had SHM embedded, then those issues would have not been detected unless the problem could have become more visually apparent, leading to any prevention of escalated deterioration. Therefore, we reduced any increasing maintenance costs with the use of SHM. Finally, the algorithm that we developed is quite efficient and effective approach. It is quite easy to understand and interpret. It is adaptable to any change in the data patterns and generalizable to new and unseen situations. And finally, it is applicable for short and long-term data from any concrete mix or any concrete structures under any exposure conditions. Thank you. Any questions?
Thank you, Harshita, for your presentation. If anyone has any questions for Harshita, you can put in the chat. Before we move on to the next presentation, which you are all waiting for, I'll pass on to Ansu, who will introduce two new office bearers for Cypro. Over to Ansu.
Thank you, Anita. And thank you, Harshita. It was a wonderful presentation. And I can see a couple of questions coming through the chat in between. I am actually the current co-chair of SY Pro. So I would like to take a moment to share an exciting update from the SI Pro committee. We are thrilled to officially welcome our two new members to our team. So first joining is our new SI Pro secretary, Dr. Pooja Nair. So Pooja, if you could actually please turn on the video, that would be great. So Pooja is a hydraulic binder chemist at Normit UK, where she develops advanced construction chemicals supporting sustainable tunneling and mining practices. Her focus on low carbon innovative solutions aligns perfectly with our mission for a more sustainable built environment. So Pooja, are you still there?
Hi everyone, I'm here and I'm looking forward to do work in this amazing group.
Thank you, Pooja. So next, I would like to welcome Anna Camelia as our new SPI Pro Treasurer. Anna, if you could actually please turn on the video, that would be great. So Anna is a site-based engineer with Morris Roy Limited, actively involved in the delivery of complex concrete frame projects. Her on-site experience and strong focus on quality and safety will be a valuable asset to our team. Welcome, Anna.
Hi, hello. I'm going to be short because it's a bit noisy in my office. So, hello everyone.
Thank you, Anna. So we are really excited to have both Pooja and Anna join us and look forward to the expertise, passion, and the fresh perspectives they will bring onto SY Pro. And at the same time, on behalf of SY Pro, I would like to express our heartfelt thanks to Anita and Anna, who were our previous SY Pro Secretary and Treasurer, for their incredible leadership and dedication over the past 2 years. While they are transitioning out from our committee roles, we are really grateful that they will continue to mentor and support us in our next phase of our journey. So thank you, Anita. Thank you, Anna, again, for all the support you have given us already. Thank you. Over to Anita.
Thanks. Thank you, Ansu, for your nice words. It has been great working with the team over the past 2 years. And I'm happy that I'll be continuing to work with the team even going forward. Anna, do you have to say something?
Yes, it was a great pleasure to be part of CyPro committee, and I'm wishing the best of luck to Anna and Pooja. We are there for any support. Any questions, anything you might need, please feel free to reach out, and look forward to seeing CyPro growing.
Yeah, I think we'll move on to the next presentation since we are running out of time, and we can address both the questions at the end, also for Harshita. So next is Oliver. Oliver Greet is a concrete technologist working at Converge, a technology company based in London. His background is in low carbon concrete products, alkali activated cementitious materials, geopolymers, and non-destructive testing. He holds a master's in advanced concrete technology and is a member of the Institute of Concrete Technology in the UK. So he's going to present today on the topic digitizing concrete. Over to Oliver now.
Thanks very much, Anita. Just share my screen. Afternoon, everyone. I'll try and fly through this as quickly as I can. I'm conscious of time. Please do put any questions you have in the chat, and we can try and address those at the end. Cool. So I work for a company called Converge. We were founded more than 10 years ago now. There's about 60 of us working in London, and we work on projects around the world. We're a sensor company, and we manufacture sensors that go into concrete and track the in-situ strength gain of concrete. And we work with lots of companies on a wide range of projects around the world. So the focus of what I'll talk today about is called the maturity method. The maturity method is a technique that dates back to some research going on over 70 years ago now. The first paper was published in 1949, looking at how the temperature of concrete affects the rate of curing. So as with any chemical reaction, the rate at which that reaction proceeds is related to its actual temperature of the system itself. And so the research into this began whilst research was looking into steam curing techniques in concrete back in the 50s, and they needed better methods than the existing techniques to try and understand the strength gain of those materials subjected to different thermal environments. So early researchers introduced this term temperature time factor. Essentially, this is just a value that relates to how progressed the hydration reaction is within the concrete itself. And they published a very simple function to help us to understand that. So I'll give you a quick example here. So in this case, we're going to take two samples of the same materials, same concrete mix design, cured in 2 different thermal environments. And the first function that's published is quite simple. It just takes the area underneath this chart, essentially, underneath each temperature profile. So in the top left case, you can see the sample curing at 15 hours, for 15 hours at 20 degrees. And in a second case, we're going to cure a sample for 10 hours at 30 degrees. And what the researchers posited was that both of these samples have accumulated the same area underneath their temperature profiles. And as a result, they share the same maturity and notionally should have a similar value of strength. What this unlocks is the ability to actually take account of varied temperature conditions as the concrete matures, and also to predict how different thermal environments will influence the rate of reaction. In subsequent papers that were published, they sort of took this technique a lot further, and I'll give you a quick example of that now. So this is the first function that was published, and what we can see here is that at 20 degrees Celsius, at any given time, we're relating the rate of concrete curing to a sample curing at 20 degrees Celsius to understand how it cures and the rate it cures, relatively speaking. So if we look at these charts, we can see at 20 degrees Celsius, that gives us an age conversion factor of 1.0. Now, if you double the temperature using this function, that tells you at 40 degrees Celsius, a sample should be curing roughly twice as quickly as a sample at 20, and vice versa at 10 degrees, half as quickly. Again, as the research went on, that was in 1951. A second function was published in 1977. Actually, Harshita referenced the same guy, Arrhenius. He was actually a 19th century chemist, so didn't publish this function, but it was named after him as he published one of the original functions in pure chemistry, looking at reaction rates and how kinetics affect those reaction rates. So what you can see here is this function is considered sort of superior than the first one. It addresses one of the main issues, which is that actually in practice, the linear rate of reaction, or the suggestion that the rate of reaction is linear with respect to temperature, i.e. it doubles at between 20 and 40 and would therefore double again at 80, doesn't actually hold entirely true for many concretes. This function is still in broad use today, but the second function allows you to adapt it for different chemistries. So particularly with the use of ground granulated blast furnace slag, or GGBS today, the actual influence on this, as some of you may know, is that it increases the sensitivity to temperature. This means as we elevate the temperature, we get a disproportionate increase versus a Portland cement concrete. And conversely, at lower temperatures, which we're more familiar with in the UK, you see a reduction in the rate of strength gain. So this most commonly in the UK manifests itself when we're curing in cold weather conditions, with high GGBS concrete slowing down more than a Portland cement concrete. It's not broadly known, but that actually, conversely, when you move up the temperature scale, you get this massive elevation in temperature with use of high GGBS concretes as well. So it's just a phenomena of concrete technology that is interesting, and many people aren't fully aware of, that we can quantify exactly how much faster or slower high replacement mixes will be. And that particularly does lend itself, with their increasing use today, to these techniques. So using this information, i.e. the rate of reaction, we need to couple that with some other information in order to obtain the in situ strength, which is really what most of our users are concerned with. They want to understand how strong their concrete is within the structure itself. So in order to do that, there is a calibration process. Essentially, the relationship between the maturity and between the strength is going to be distinct for every different mix. And so this can be determined by casting some samples and curing those in standard conditions. And you get a curve, as you can see here, and this, coupled with the information I just ran through, can be used to develop predictions of the in situ strength condition itself. And so just a quick note here on the maturity method versus traditional test methods. So traditional test methods, we use cubes in the UK, cylinders are used in Europe and much of the rest of the world, is a really useful technique. And I don't like to speak ill of it at all. It's obviously essential for proving long-term strength, and most specifiers are going to specify concrete according to its cube strength, cured in standard conditions. This is particularly useful when we're in the production of concrete, when we're establishing or assessing how the strength gain of concrete varies over time, perhaps due to material variation. And that should give you the same answer year round, really. You want to understand how these materials combined behave in standard conditions. But for the contractor on site, it's not entirely useful in terms of understanding how the concrete within the element itself is gaining strength, particularly in extreme seasonal environments. So it should give you a good indication of the strength potential of the concrete, but not actually tell you how strong the concrete within your structure is. And that's where the maturity method tends to come into play, and it's generally used by contractors who are looking to perform activities at early strength, at low values of strength, which are considered really time critical for the project. So examples of that include removal of formwork, application of post-tensioning, or in precast factories, the lifting of concrete or removal of those molds. These are all really time critical and will affect the overall delivery time of the project. And so that's where we tend to see the maturity method being used. So I'll run through a quick example here just to illustrate exactly how it's working. So we've established our calibration curve here. This was done using cubes cured at 20 degrees Celsius in standard conditions. A number of crushers that have been taken and this curve is generated. Now the contractor in this case is looking to perform something like post-tensioning, and they're looking to obtain that key strength of 25 megapascals, which in the calibration was observed at 48 hours from the cube samples. Now, coupled with sensors being cast in situ, we can place those into the element itself and see how warm or cool the element is, which is really going to be dependent on how thick the element is, as well as the seasonality, so the effect of ambient temperature conditions. And we know, using that temperature information, how fast or slow the concrete is actually moving along its calibrated curve, and when we're going to obtain that 25 megapascals. So we'll take a summer example here first, and you can see in this case we've poured the concrete at an initial temperature of 16 degrees Celsius, and then due to the thermal mass of the element itself and the exothermicity of the material, that's gained temperature through time. And you can see here it has a peak temperature of 37 degrees Celsius and then cools back off to its environmental condition over time as it loses its exothermal heat to its environment. And you can see here, well, the cube stored at 20 degrees Celsius was actually achieving 25 megapascals in 48 hours. You can see here, actually, due to the elevated curing temperatures, that accelerates for the structure itself. In this case, a reinforced concrete slab or a post-tension slab is going to be curing slightly warmer than the samples, and therefore that's accelerated the amount of time, or reduced the amount of time and accelerated the rate of curing. And we can see that 25 megapascals is actually achieved in about 26 hours in this case. I'll take now a winter case. So we're pouring concrete at a temperature of 7 degrees Celsius. And as a result, it doesn't actually give off quite as much heat, and it never quite goes over its 20 degrees Celsius threshold at which we're curing our standard condition cubes. Now, in this case, actually the cubes will continue to obtain 25 megapascals at 48 hours, but this is actually a slightly artificially accelerated picture of the true strength development. The in situ concrete, which is slightly cooler, is going to take longer, and as a result, that's going to take 72 hours. So this gives you a sort of understanding of the summer and winter cases and the merits of using sensor-based monitoring to track the strength gain in each condition. Ultimately, the cubes themselves are going to give a slightly incorrect picture of how the concrete is gaining strength, and that's particularly relevant in these first 24, 48, 72 hours, while we see a lot of that thermal activity from the concrete itself. So here I've got some data collected from our sensors. So as I said, we've installed over 30,000 sensors now. This was an analysis I ran a couple of years ago based on slabs cast in the UK. And you're looking at the curing temperature, the average curing temperature of those slabs over the first 3 days of curing. And this is all in the UK. So you can see here, actually, again, our standard curing temperature of 20 degrees Celsius is highlighted. And actually, the thermal condition of the concrete over the first 3 days, on average, can vary as high as 34 degrees Celsius here in July, and down as low as 12.5, 13 degrees Celsius in winter. In the chart on the bottom right-hand corner, I've run that through the maturity functions I showed you earlier to get an appreciation of the curing rate and as a consequence of that thermal environment. So again, this is essentially the relative rate of curing versus a cube stored at 20 degrees Celsius. And you can see here in the middle of summer, the concrete within the element itself can be curing around twice as quickly as the cube might otherwise suggest. And conversely, in winter, it might be curing sort of 30 or so % slower. So this really highlights why contractors in particular see a merit in using sensors to track strength gain in particularly time-sensitive elements. It can both be a question of accelerating their productivity on site, where they want to take account of the fact that the in-situ concrete is actually curing much faster than traditional tests might suggest. But also there's a safety aspect as we go into winter, where we're looking at applications like post-tensioning slabs. If they are operating that based on the results from a cube stood in standard conditions, they'll get artificially elevated strengths. And as a result, that might lead to safety critical incidents like the breaking out of tendons or anchors. So the maturity method is standardized in an American standard. This is where it's largely been used over the last few decades. And that covers all sorts of things like the functions I've talked through, the use of calibration, system requirements, and so on. That's called ASTM C1074, and we largely reference this standard. It's the de facto standard used around the world when using the maturity method. Our system itself is a sensor system, as I said. So sensors are placed within the concrete elements. They track the thermal condition, and then that's transmitted to the cloud, where that's all converted to the strength of the concrete itself, and that can be accessed on a smartphone or on a computer from the web platform. There you can take a look at sort of the in-situ condition of the material itself over time. So you can see here a pour that's taken place and the thermal development on that pour, as well as the blue curve, which represents the strength gain. And then contractors will specify key strengths or milestones which they're concerned with, and the system tracks those. We can also use it for tracking of thermal temperature differentials. So this is a common use case for raft concrete slabs and any other mass concrete applications, where the thermal differentials will be usually specified in there. And so you can use the system to track the concrete in various locations. We have a couple of flavors of our hardware. I'll fly over these because we don't have much time, but we have a Bluetooth system, as well as a long range system we've recently developed. And also just to mention, we have an AI system which is used to predict the exact times at which strength are going to be obtained. So we're trying to bring as far forward in the process this information as possible. So the maturity method itself allows contractors to understand the strength development in real time, and we're using data analytics to try and bring that information further forward in the process, so they, instead of still reacting at the time that strengths are achieved, to try and plan around the expected strength behavior of their concrete. I've got a couple of case studies to fly through quickly, and then I'll probably wrap because we're conscious of time here. This is a project we worked with Careys and Multiplex in London. This is a 50-story tower with a very tight program, and you can see in the bottom right-hand corner, this is their jump form, rising formwork system, where they were using us to track the strength gain. As I say, it's a common use case where we see time critical, where we see the strength gain of the concrete in situ essentially forms the rate limiting step and is considered time critical. So they used it in post-tension slabs as well as in their core system, and they attributed a day of saving per floor due to the elevated temperatures they observed and having access to real-time data. So over 50 stories, it accumulates a considerable time-saving potential. This is London City Airport, and we worked with them over the last 2 years and actually developed our first AI system on this project. So you can see there, this is before our involvement. On the right-hand side, London City Airport just had a runway, and so planes would have to turn around on the runway and then take off. So it's not an entirely efficient process. We helped with the construction of a new apron that's been there for a couple of years now, and that has a taxiway as well. So now it over doubled the capacity of London City Airport. The system again was used as it got limited access there to try and establish the strength gain of the concrete in situ on their new concrete apron as early as possible. And again, we developed an AI which helped them try and predict that all ahead of time. That's a new civil engineer cover that we got at the time. I'll probably skip over this one because I think we're probably running short. Ultimately, the system is useful in a wide range of applications. Like I said, twill towers and things are usually our bread and butter, but we work on a lot of civils, as I just showed you, and this is a case where we were helping the London Underground in some very time-critical repair works where they tear out the concrete and cast it in. Those tracks need to be operated again by Monday morning. Usually you get a 24-hour window, so again, very time-critical, and we saved over 12 hours ago there. Some quick mentions. So we're developing a data system for concrete. This ultimately tracks the strength results of concrete, so traditional cube measurements, and any deliveries of concrete to the site. So any QA data that's associated with the concrete being obtained on site, as well as the embodied carbon. Happy to talk with more people about this afterwards if they're interested. And then Mix AI is a system that we're currently developing, looking at predicting the performance of concrete ahead of time, and also looking at how we can adjust concrete mix designs to make them more optimal in terms of carbon and performance. So with that, I will yield the rest of my time. I think I've just about brought it in time. So thank you very much for listening, and I'm sure we can perhaps take any questions if we have none.
Thank you, Oliver. That was a wonderful presentation. We have one question for you from Raman. Has this method been used for AACM concrete? And I assume with LC3, you will need to establish database to predict from your measurements.
Thanks very much. So the technique itself has been used in a wide range of concretes. I mean, it's a method based on empirically proving it with the system. So with the specific concrete material. So the method itself was developed over decades, largely with Portland cement systems. And as the use of GGBS has grown increasingly prevalent in the industry, it's been demonstrated to be effective across a wider range of mix types. And we have indeed monitored several cases of alkali activated systems. And in that case, it just takes the judgment of the practitioners as to determine whether or not we're seeing a good relationship between the rate of strength gain and any other test data that we have available. So it needs to be slightly more scrutinized when it comes to the use of this technique with novel materials. But we have done that and satisfied various consultants that the method can be applicable. As I said, the technique is actually really useful for high replacement materials since they're often more sensitive to their curing environment. I know I was actually involved many years ago in the development of an alkali activated cementitious product. I've got Professor Hewlett here as well, so lots of people who know lots about it. But we were finding at the time low curing temperatures observed in winter can make it really challenging. And actually, as I said, high replacement materials, that's a common phenomena. And we find that using the maturity method, using sensors coupled with high replacement mixes, allows you to more tightly understand the rate of strength gain in low or high temperature curing environments.
Yeah, thanks, Oliver. And I have a question for you. Like, as part of your case studies, have you done any studies on how much carbon savings you can get from reduced time of construction? Do you have some numbers related to that?
Yeah, that's an excellent question. I mean, so for the most part, what I try and do is with the sensors is allow contractors to accelerate program, allowing them to be more ambitious with, let's say, their replacement level. So in really time sensitive applications, they want to move as quickly as they can, and so often, and they're often been bitten in the past by high replacement material slowing them down. So really, for me, it's a question of allowing them to, maximize productivity in other ways, so they can continue to be aggressive there. In terms of the carbon savings directly attributable to speeding things up, that's mostly a question of reducing the amount of time generators are running on site, the number of trips to site, and these are valid, but I think they're much smaller in their impacts over the course of a few days than any decision on the material front. Whereas like increasing GGBS by 10% can have a really notable impact on the overall embodied carbon.
Yeah, most of it's the carbon, cement is the carbon hotspot, isn't it? Yeah. And I think Harshita has answered most of the questions in the chat. Are there any left to be answered? We can answer it now. There is a question from Bob Clark. Considering the non-variation in activation energy with hydration age, water to binder ratio, and the proportion or type of SEMs used, how valid is it to apply a constant activation energy in maturity-based strength models for modern ternary or low-carbon concretes? Harshita, do you want to take that?
I think that's a question for Oliver.
Happy for Harshita.
Okay. Yes.
So many
Sorry.
lessons
Before
to learn
answering
there.
in more detail, then I.
It's an excellent question. I mean, there's still ongoing research on both the maturity method and its applicability in a wide range of mix types. I think one of the broadly recognized things is that the principle of an activation energy in a multi-phase system of a single value of activation energy in clearly what we all understand to be quite complex chemical systems, does need to be considered and assessed. Yeah, I won't go into huge depth given the amount of time we have available here on the answer. Happy to talk with Bob about it separately. But yeah, in general, I think in the case of ternary systems and their specific niche behaviors and interactions, let's say, I think that probably needs to be further assessed. At the moment, ternary systems are accepted by the American standard. And so the maturity method can be used with them, but it really does take the assessment from the relevant practitioners to make sure that it is suitable in each case.
Yeah, I think there is another question from Bob Clark. Yeah, actually, I meant to read that and accidentally read this one. Yeah, it's on, I don't know if you have answered this already, Harshita, given that electrical resistance readings are heavily influenced by mixed composition, particularly the use of SCM such as GGPS or fly ash and chemical admixtures like accelerators or retarders. Can these influences be reliably quantified or normalized to allow for accurate interpretations across varying mix designs?
Yeah, I've answered this as well, but so basically, the methodology that we have developed, it's been applied on different type of concrete mixes, be it GGPS, a PFA, or